Okay, we're getting here towards the end, and so for those who have and those who haven't, we have to hit some level of competency and prove that for you to finish the course. And so part of that competency, I would have to say, would be being able to ask yourself a question that you know the answer to. So I've got 10 problems here, forms of problems that form the basis of the Strength of Materials course and a large basis of the other course as well. We'll be looking at alternative assignments for those of you who have not turned in a homework or have just turned in homeworks that were a scribbled copy of what was put in the book, and also for exams, and this will be a portion of that. So let me look here at the first form of the problem. First form of problem, let's look at this. How about this? Something hanging on a cable when it is underwater. First form of problem is a simple tension problem when you've got both weight and buoyancy. And for now, we'll put that all the way underneath the water. And what does the free body diagram look like? What is touching it? Tension. What is quote-unquote touching it? Weight. And what is touching it up, going this way, is the buoyant force. Tension is what you measure. Weight can be measured by knowing the mass, and the buoyant force equals the volume of displacement times the unit weight of the water. That's a form of problem that you can then do a couple of riffs on. Problem number 2, form of problem. Something very similar, held up by 2 wires, 1, 2, straight up, and that you know that the weight down is mg, and that you know T plus mg, with mg being negative, minus mg equals 0. That's a second form of problem, believe it or not. The third form of problem would be something that has a weight down, mg, and cables held up at directions of 45 degrees and 135. And you would know that the y component of each of these would be mg over 2, which means the x component would be mg over 2, which means you can solve for the tension in the cables. That's a very similar problem to what we know, that the sum of the forces in the x equals 0, and the sum of the forces in the y equals 0, and that every force is equal to its force. The x component is every force is the force times the cosine of theta, if we call it force 1, and y is force 1 times the sine of theta 1 in a two-dimensional world. So that is the third form of problem. And you could riff in on any one of these. So this is a basic buoyancy problem showing that you have any number of forces, but mass causing weight, and then buoyant force up, and then a cable force shown as tension. You'd have this idea of cables acting up and down, which can be riffed on. In this case, tension, each tension equals mg, or the weight, over 2. You can do the same thing here and then riff off on that. Again, answering questions you know the answer to when you're solving methods. Let me go down to a new file, new slide here. All right, those are the basics of concurrent force problems. Let's add the fourth one of a concurrent force problem. And that, of course, is a joint. When you have a joint with reaction force on it, I'll show the reaction force here, and for instance in some sort of truss, those act very similar. You'll again show the tension here and here, and you know that the sum of the forces in the x equals 0, and the sum of the forces in the y equals 0. Or you know that the externals, tension 1 and tension 2, are the opposite of the internals of the reaction. So we're going to call this problem 4. So we know that we can write a matrix that looks like this and use the RREF function, or more likely what we can do is we can do a problem like this. We can slide it up here, our known force, pick a direction home, and get there along two known forces. So this form of problem is a concurrent force problem. It comes up again in a method of joints once you're in the middle of method of sections. All right, let's go to the ones we know for beams. One is this, a simply supported beam with a span L and a force P on it. The reactions are P over 2, P over 2. The shear is P over 2 down P and over here, and the maximum moment is PL over 4 because it's this area of shear. So that is a point load. Number 6, a uniformly loaded beam, something under self-weight, of length span L and load W per foot. We know that the maximum moment equals little w times L squared over 8. And we know that the reaction is, of course, WL over 2, WL over 2, which means, of course, that the shear diagram begins at WL over 2. It comes down, comes back up, and the moment diagram is a parabola. The moment diagram here was a triangle. That was problem number 6 in terms of knowing. Basically, you just know the answers, and later on you can figure out the methods. Remember, our method will be to cut the structure at any one point and ignore what's behind us and translate our coordinate and just add up the moments and the forces of everything that is external. Let's go to a new problem. Problem number 7 would be something like this. Let's assume you had a deep truss, something like in the gym when you're graduating, and you had a force on it, something like this P here. Of course, you had P over 2 and P over 2, and you want to know what are the forces of compression and tension just to the left here of that force. Well, what do you know? Well, you know that P over 2, we'll call this span L, P over 2 times L, so this force here times this L over 2 is PL over 4, and you know that PL over 4, that moment has to be resisted by something D, so you take PL over 4 and divide it by D, and that'll get you your force P inside the truss. So what you have to know is that this force times this distance equals one of these forces times this distance. Now, that force, of course, is P over 2, so you can riff on that a little bit. But the fact that force times distance here is the same as force times distance here, of course, these are equal and opposite. That's number 7. Number 8 is very similar. We looked at it a number of times. That's something, for instance, that's out of some sort of truss or some structure that's a pin joint and a roller joint, a truss out here with a force P down. We know that the reaction here is more, and it's based on a ratio of L to that depth there. So the reaction equals P times the ratio from here to there. Again, you know the answer to that one. It's the logical one of force times distance and more or less. That is problem number 8 we should know. Know as in sight. Know as in then you can come back and check some of your methods. Let's try another one here. That was number 8. We're going to do number 9 going back. Number 9 was a cable under a uniform parabolic load. of W. It was L long, therefore this was WL over 2. This was WL over 2. This tension, horizontal tension here, you cut it here, and you know that this is true. WL over 2 times L over 2 minus, of course, this WL over 2 down. You end up with something that looks like this. WL squared over 8 equals the tension times the sag. We'll end it there and pick up on problem number 10.